So the other electrochemical cell is called an electrolytic cell, and it uses electricity to do the opposite of a voltaic cell. Remember, a voltaic cell uses the spontaneous energy released by a redox reaction to generate electricity, but an electrolytic cell uses electricity to force a non-spontaneous redox reaction to occur. Being non-spontaneous, it's a good bet that it's endothermic, which is why the electricity is needed. So the word electrolysis means electricity and breaking, so you're breaking down a compound, an ionic compound, using electricity. So the electrolyte is an ionic solution, or it can be a molten ionic compound if the melting point's not too extremely high, where the reactants, in this case the ions, are found in the solution, and they're going to be oxidized and reduced at the two different electrodes. So the electrolyte is the ionic solution. The electrodes are the metals that conduct electrons or electricity, and the place where the oxidation and reduction actually take place. So the ions are going to be drawn to the electrodes, and they're either gain or lose electrons here. So we say ions are discharged at the electrodes, and by discharge we mean they lose their charge because they either gain the missing electrons or they give up the extra electrons. Reactive metals, so all of group 1 and 2, and many of the transition metals, exist in nature as positive ions. They're in some kind of compound. You don't find pure metals that often in nature other than gold and some silver. So if there's a good reducing agent that you can use, you can add it to the ionic compound and get your metal out of it. But not all metals, in fact many metals, don't have a good reducing agent available. So in those cases, we force reduction by using electrolysis or by running electricity through it, adding the electrons back to the metal to force them to be reduced. And this can be used to extract nonmetals as well as metals. But with nonmetals, we remove the extra electrons. So two other procedures that are very similar or use this idea of electrolysis are the idea of electroplating and something called anodization. So what are the components of an electrolytic cell? Really very much like a voltaic cell, because you need the electrolyte and you need the electrode, so you have metals and you have ionic solution. But now you also need a power source, you need a wire to connect it all, but you don't need a salt bridge. So the power source is going to be a DC power source, a positive end and a negative end, and so the symbol for that is shown with a long line and a short line, and the longer line represents the positive terminal. Again, the electrolyte's the liquid that conducts the electrical energy, and it undergoes a change because that's where the ions are that you want to reduce or oxidize, usually into a pure metal or a nonmetal. And then the electrodes are made from metals or graphite, and they're immersed in the electrolyte to conduct the electricity externally and complete the circuit. But you have to be careful that you have what are called inert electrodes. You want to make sure you have a metal that's not going to take place in the reaction. So you need a less reactive metal for those electrodes. And then finally, you need wires to connect the power source and the electrodes together. So unlike a voltaic cell, an electrolytic cell all takes place in one cell or one container. And the power source, you can see it up on the top, here's the symbol for it, is going to push electrons toward the negative electrode, and that's where reduction is going to occur. So here I see the electrons being pushed out. Let me get my pen here. Electrons being pushed out from the negative end of the battery. Electrons are going to pile up at the cathode, and since gaining electrons is reduction, cations are going to be reduced here. So your metal ions could come and be reduced at the cathode. And then the electrolyte has ions in it, and some ions aren't participating in it, but the anions are going to be drawn over to the positive end, and the positive anions then, or the anions, the negative anions, such as maybe chlorine, are going to be attracted over to the positive side, and they're going to be oxidized at the anode. Remember, we said earlier the anode is where oxidation always takes place, and in the voltaic cell, it's at the negative terminal. In this case, it's at the positive terminal because the anions get oxidized at the positive terminal. So an NaCl solution would provide chlorine ions to the anode and sodium ions to the cathode, and you'd end up with sodium metal precipitating out and Cl2 gas being produced and possibly escaping. So if I clean up my mess here, and if we draw in some NaNCl, we've got electrons piling up here. That makes this end more positive because of the potential difference there. We have sodium ions and chlorine ions in our solution. So the sodium ions are going to be drawn or attracted to that negative end. And at that point, we're going to see the sodium ion pick up an electron and become sodium metal. At the same time, we're going to have chlorine anions precipitating over here. They're going to be giving up their electron and forming chlorine gas. And you could have some kind of contraption here to catch that gas, or you can let the gas escape, whereas the sodium metal will plate right onto the electrode. But that's why salt water is so corrosive to many metals. So again, electrolytic cells, it's the reverse process or purpose of a voltaic cell. Instead, you're using electricity to force redox to occur instead of producing electricity. As I mentioned earlier, the anode and cathode charges are reversed from a voltaic cell because an anode and cathode get their name from the process that happens at each. A cathode is where the reduction takes place, and the anode is where oxidation takes place. So since the electrons flow from the power source and reduce metals at the negative terminal, that is the cathode. Whereas the anode is where anions from the solution deposit or lose electrons, and that is where oxidation is taking place, even though it's the positive terminal. What are some uses of electrolysis? Well, molten salts are often separated with electrolysis for both metals and nonmetals that get freed up. Most salts have really high melting points, so it requires a really high temperature and lots of energy to do this. But it allows us to predict both the products and the electrode at which each is going to be produced. For example, it says, describe the reaction that occurs at each electrode and any physical changes you'd likely observe when molten lead bromide, a bright blue liquid, undergoes electrolysis. Write a balanced equation from the half equations. So this is a pretty typical question for IB for you about electrolytic cells. So let's tackle it here. I'm going to sketch, first of all, lead bromide. Lead 2 is going to be PbBr2. So we know we're going to end up with lead and with bromine gas. So this is going to become a gas. This is going to become a solid. This is aqueous or molten. I guess it's liquid technically. So what's going on here? Well, Pb is going from a +2 oxidation state to 0, and bromine's going from a -1 to 0. So that gives us a hint about what's being oxidized and what's being reduced. We've got electricity being pushed out, so that means my Pb2+ must be gaining 2 electrons to become solid lead. And at the same time, my 2 bromine ions must be giving up 2 electrons, 1 apiece, to form the bromine gas. So first of all, any physical changes, describe the reaction that occurs at each electrode. So which electrode is this? Well, this is reduction. And reduction happens at the cathode. This is my oxidation. So this must be occurring at the anode, because oxidation always occurs at the anode. And then what physical changes would we see? Well, since this is a bright blue liquid, we're going to see it losing its color, and we're also going to see the gray metal appearing. We should also have a gas that we're collecting. So all those would be changes. The loss of the bright blue color, the appearance of a grayish metal, and the appearance of a gas. And then to get my balanced equation is actually pretty easy from this, because it's lead 2. I've got 2 electrons on each side. I don't have any oxygen or hydrogen I have to account for. So I really have Pb2+, 2Br-, forming Pb solid, and Br2 gas. And I could leave these as separated, leave it as a complete ionic equation, or I could go ahead and rewrite that as PbR2. So just some fun facts to wrap up electrolysis. You maybe have heard of electrolysis for hair removal, and it works by producing sodium hydroxide during the process, and that ends up killing the hair follicle. Aluminum, you probably know, is a widely recycled metal. It's one of the few things you can recycle and get paid for it. It's the second most used metal in the world, and it is the most recycled. However, electrolysis to obtain aluminum is incredibly expensive and energy intensive. So even though it's the second most used metal, it's recycled for that very reason. Recycling aluminum uses 5% of the energy and only produces 5% of the greenhouse gases compared to trying to get aluminum through the electrolysis of its mineral ore called bauxite. Electroplating is another use of electrolysis where you layer one metal on top of another. So this is often done for decoration, like maybe candlesticks or something, or jewelry, or even silverware, where a thin layer of the expensive metal is layered on top or outside of the less expensive metal. We also do this for protection. We call it galvanizing sometimes, like when we layer zinc over iron, and it protects the metal underneath by putting a metal outside that will react with the oxygen or whatever is out there first and protect the metal underneath, which is giving the structure, say, its strength and its stability.